Let's discuss Unit 5 solutions. At a particular time of computation, the value of a counting semaphore is 7. Then 20 P operations and X number of V operations were completed on this semaphore. If the final value of semaphore is 5, what will be the value of X? P operation is for wait and V operation is for signal. So whenever there is a P operation or a wait operation, you have to decrement the value. Whenever we have a signal operation or a V operation, we have to increment the value. Usually they will ask you the final value of semaphore, but this time they are asking you the value of V operations count. So the initial value of the semaphore will be 7. The number of P operation will be 20. The number of V operation will be denoted by X and the final value of the semaphore is 5. Initial plus V minus P is equal to the final value of the semaphore. So instead of initial I am substituting it by 7. Instead of V I am having it as X. Instead of P I am using 20 and instead of the final value I use 5. So 7 minus 20 will be minus 13 is equal to 5. X is equal to 5 plus 13. X is equal to 18. So there are 18 V operations. Option number 3, 18 will be the right answer. Next question. In a multi-user operating system, 20 requests are made to use a particular resource per hour on an average. Per hour, 20 requests. The probability that no request is made in 45 minutes. An event can occur 0 time or 1 time or 2 times in an interval. Average number of events is equal to lambda. So this lambda is also called as event rate or rate parameter. The probability of observing k events in an interval. So here we can place 1 time, 2 times or k number of times denoted by P of k events is given by the formula lambda power k e power minus lambda divided by k factorial. K denotes the number of events. So here event is equal to the request made. Since no request is made, we are mentioning k is equal to 0 for this problem. For 45 minutes, k is equal to 0. So we have to find lambda. Lambda is equal to 45 into, for 1 hour we have 20 requests. So 20 divided by 60. 45 is also in terms of minutes and 1 hour is also converted to minutes. Dividing by 60 we are converting it to minutes. Now if we cancel this 0, 2 into 3 times, 3 into 15 times, lambda is equal to 15. So the average number of events will be 15. Now we will find the probability no requests for 45 minutes. P of 0 is equal to lambda power k e power minus lambda divided by k factorial. Let us substitute the value. 15 power 0 e power minus 15 divided by 0 factorial. 0 factorial is equal to 1 and 15 power 0 is also equal to 1. So the final answer will be e power minus 15. Option number 1 will be the right answer. Next question. Consider the following table of arrival time and burst time for 3 processes P0, P1 and P2. The preemptive shortest job first scheduling algorithm is used. So whichever job is having least or short burst time will be executed. They have used the term preemptive. It means you can take 2 processes. One process is coming with 3 burst time and the second process is coming with 2 burst time. At arrival time 1, this will be executing. Once I get the second process with a lesser burst time, I can preempt to this process. It means I can shift to another process. So preempting is I can give the CPU to another process. Scheduling is carried out only at arrival or completion of a process. What is the average waiting time for the 3 processes? So let's use a Gantt chart here. So we'll start with 0. At 0 milliseconds, P0 is arriving with a burst time of 7. I am executing it for 1 millisecond. At time 1 millisecond, P0 will have 7 minus 1, 6 burst time, and we have another process coming in P1. P1 has a burst time of 3. Now we have to choose the one with the shortest job. So here P1 gets selected and we are preempting it to the next process. This time it will be P1. At time 2, we will have P0 is equal to 6. P1 is equal to 3 minus 1, which is equal to 2. We have another process coming in, P2 with the burst time 7. Now if we choose the shortest job, it is P1 again. So we can complete P1. Again and again it is going to be reduced only. So at time 4 milliseconds, P1 will complete its job. You can even put for 3. When it is 3, P0 will remain 6, P1 will have 1 and P2 will have 7. Again we are choosing this. At 4 we will have P0 is equal to 6, P1 is equal to 0. It means the job is over and P2 is equal to 7. Now select the shortest job again. We are going with P0. Again when you keep decrementing by 1, P0 will be executing continuously. So I will place P0 in this Gantt chart, and for 6 burst time it will be executing. So 4 plus 6 around 10 it will complete. After P0 is over at 10, we will have only P2 process with 7 burst time. So P2 will execute from 10 to 17. So around 17 all the 3 processes will be completed. Let's calculate the waiting time for the processes first, then we'll take the average. You can do this in two ways. First way, you can find the completion time. P0 is completing in 10, P1 is completing in 4 seconds and P2 takes 17. So this will be the completion time of all the 3 processes. From this we have to find turnaround time. This is nothing but completion time minus arrival time. 10 minus 0 is 10. 4 minus 1 is 3. 17 minus 2 is 15. From this we will calculate waiting time. This will be the difference between turnaround time and burst time. So 10 minus 7 is 3. 3 minus 3 is 0 and 58 minus 7 will be 8. In short, without getting detail into this chart, we can also find. Just find when is P0 starting. It came at 0 and it started immediately. Again, in between it has waited for 3 milliseconds. So the wait time of P0 will be 3. Again it started its execution at 4 and it continued till 10. So there is no wait time and the process got over. For P1 there is no wait time at all because it came at 1 and it got executed completely. So in this case P1 will have 0 waiting time. If you take P2 at 10th millisecond it started its execution and it completed at 17. But when did it arrive? It arrived at 2 milliseconds. So 10 minus 2 will be 8. 8 milliseconds will be the waiting time. You can either calculate like this or you can use this turnaround time and then calculate wait time. It is all up to you. Whichever way you are comfortable you can carry out. Now we will find the average waiting time. Totally there are 3 number of processes. 3 plus 0 plus 8 which is equal to 11 divided by 3 and this will give approximately 3.67 milliseconds. Option number 2 will be the right answer. Next question. Consider a disk system with cylinders. The request to access the cylinders occurs in the following sequence. Assuming that the head is currently at cylinder 50, what is the time taken to satisfy all requests if it takes 1 millisecond to move from one cylinder to adjacent one and shortest seek time first policy is used. So from the diskette I have to take the shortest seek time. So let's place the sequence in ascending order. Head is at 50. It can either move to 34 or to 73. We have to calculate the shortest seek time. So 73 minus 50 will give 23 and 50 minus 34 will give 16. So we are going with 34. 50 to 34. From 34 I have to travel back to 73 or 20, which is short. So from 34, only 14 movements are needed to go to 20. So we are choosing 34 to 20. So here the movement number is 16, here it is 14. So hereafter we need not touch 73 because 20, 19, 15 will have shorter time. 20 to 19 it is 1, 19 to 15 it is 4, 15 to 10 it is 5, 10 to 7 it is 3, 7 to 6 it is 1, 6 to 4 it is 2, 4 to 2 is 2. Once it reaches this end, then it will travel back to the next end. So from 2 it will move to 73. So in between we have 71. This will be a total of 119 milliseconds. This is the total head movement. Now we have to calculate the time taken to satisfy all requests. To move from one cylinder to another cylinder, the time taken will be 1 millisecond. Time taken to satisfy all requests, or in short we can say the total seek time, equal to 119 into 1, which is equal to 119 milliseconds. So option 1 will be the right answer. Consider the following statements. Statement 1. LRU, least recently used page replacement algorithm, suffers from the Beladi's anomaly. Let's first understand what is Beladi's anomaly. It's a phenomenon where increasing the number of page frames results in an increase in number of page faults. The page replacement algorithms that are experiencing this anomaly will be FIFO, first in first out, second chance algorithm, random page replacement algorithm. So in this list we don't have LRU, so S1 is false. S2, shortest remaining time first, SRTF, may cause starvation. When the process doesn't get CPU, it is called starvation. SRTF will cause starvation for long CPU burst process because they never get the CPU. Why they don't get CPU is because shorter processes keep coming. So the algorithm says it is shortest remaining time first. So whenever a shorter process comes, those processes will be getting the CPU again and again. And because of this, longer burst time process will never get the CPU. When such a situation is existing, we can say it suffers from starvation. S2 statement is true. This may cause will denote the longer process will be suffering. S3, stack is shared by all threads in a process. See, regarding thread we have a statement. Every thread has its own stack, register and program counter. Only the address space is shared by all threads for a single process. So here the statement stack is shared by all threads is false. So S2 is true while S1 and S3 are false. Option number 2 will be the right answer. Given below are two statements. One is labeled as assertion and the other is labeled as reason. Assertion says input output protection is ensured by a hardware trap. Trap is nothing but a software interrupt. Reason, input output interrupt caused by the condition like IO completion and device malfunction occurring within the IO devices. Normal user programs are prevented from handling IO directly by IO instructions. It means the user programs don't give IO instructions directly. Then who takes care of it? System calls take care of it. In other term, we can say IO protection is ensured by OS routines, operating system calls. A is wrong because it is not ensured by hardware trap. There are 2 points in this. The first point is for CPUs having explicit IO instruction. IO protection is ensured by having IO instructions privileged. But in a CPU with memory mapped input output, there is no explicit IO instruction. In that case, the IO protection is ensured by the operating system routines. So this statement is the exact cause for marking A to be false. So in general they used to say all the interrupts are handled via system calls. That's why in the starting I said normal user programs are prevented from handling IO directly by IO instructions. So let's look at R. IO interrupt caused by the condition like IO completion and device malfunction occurring within the IO devices. This statement is actually true. These two conditions, whether it's IO completion or device malfunction that occurs within the input-output devices, they cause interrupt. Option number 4. A is false but R is true will be the right answer. Next question. Given below are two statements. One is labeled as assertion and the other is labeled as reason. A process involves a library function to create a thread. This is true. The threads make system calls to convey their resource and input-output requirement to the kernel. This is also true. Now we have to find whether R is the right explanation of A or not. Actually, processes start with a single main thread. The main thread can create new threads. A process can have multiple threads. Threads take less time to terminate as compared to process. One process has so many threads. The job will be split to multiple threads. So automatically thread will take less time to complete or to terminate compared to the whole process. Here they are saying the process is involving a library function to create a thread. This is about creating a thread from process using some system call. Here they are saying the threads make system calls to convey their resource and their requirement to the kernel. This is about the thread and this is about the process to create a thread. This is actually not an explanation of A. So in this case we are marking option number 2. Both A and R are true but R is not the correct explanation of A. Next question. Again we are given two statements, one with assertion and other with reason. A virtual memory system uses first in first out FIFO page replacement policy and allocates a fixed number of frames to a process. Increasing the number of page frames allocated to a process sometimes increases the page fault rate. This is nothing but Beledi's anomaly. We saw FIFO is also experiencing this. So assertion is obviously true. The reason, some programs do not exhibit locality of reference. What is locality of reference? It is a phenomenon in which program tends to access same set of memory locations for a particular time period. So this property is generally shown by loops and subroutine calls. Some programs do not exhibit locality of reference is also true, but there is no connection between FIFO replacement and locality of reference. So we can mark both A and R are true, but R is not the correct explanation of A. There is no relation between A and R in concept of page replacement. So they are talking about virtual memory system and FIFO replacement policy. Assertion is related to the statement given above it, but the reason is not supporting the assertion. Next question. Given below are two statements. Which of the following statements are correct with respect to virtual memory? First statement. Address translation is performed for every logical address used during the execution of a program. Translation from logical to physical address is performed by operating system's memory management unit. This part is true. Second statement, a program can execute only when all of its components are loaded in the memory. We have to find whether this is true or not with respect to virtual memory. Before that, we'll first see about dynamic loading. Dynamic loading is the entire program and all data of a process must be in the physical memory for the process to execute. This is with regard to physical memory. Here we have to answer with respect to virtual memory. Virtual memory is a technique that allows execution of processes that are not completely in memory. Programs can be larger than the physical memory. In fact, with virtual memory, a system can load larger or multiple programs running at the same time. A program can execute only when all of its components are loaded in the memory is true for physical memory, but with this point we can say statement 2 is false. That's why they have given in the starting as with respect to virtual memory. So statement 1 is correct, but statement 2 is incorrect. Option number 3 will be the right answer. Next question, match list 1 with list 2. So first we'll start with deadlock. Each process must be waiting for some resource, and that resource will be held by another process, which in turn is waiting for the first process to release the resource. So if you take process 1, it holds resource 1. This resource 1 is needed by another process P2, but P2 is holding resource 2, which in turn is waiting for the first process to release resource. It is a circular wait. Deadlock will be mapping to 4. So we will rule out option 1 and option 4. Now let's check working set. Working set is the memory being accessed frequently by an application. There is one term that will also refer to the same set of memory. It is principle of locality. Elements in close proximity are referred. Similar to the explanation we saw for locality of reference. Working set will go with principle of locality. So C is mapping to 3. Now we have critical region and wait or signal. So first we will find what is horse monitor. Horse monitor is similar to semaphore. It has the ability to lock or wait for a lock to view data. The work will be similar to semaphore. We will map wait or signal to horse monitor. B1. So again we can rule out option number 3. Option 2 will be the right answer. So critical region will be obviously mapping to mutual exclusion. Mutual exclusion implies that only one process can be inside the critical session at any time. If any other process requires the critical section, they must wait until it is free. Since we have mentioned about critical section, we are mapping critical region to mutual exclusion. With this, we are completing Unit 5 questions.